technological process for the manufacture of radio-controlled airplanes. The manufacture of radio-controlled RC airplanes is a multidisciplinary technological process that combines principles of aerodynamics, mechanical engineering, electronic engineering, materials science, and software control systems. This detailed process can be divided into several main stages: idea development, design, material selection, component integration, software and control systems development, assembly, testing, and iterative improvements. Below is a detailed analysis of each stage. An idea development. The process begins by defining the mission and purpose of the remote-controlled airplane. Whether the project's goal is entertainment, aerial photography, aerobatics, educational demonstration, or UAV research, this will significantly influence design decisions. Main mission, definition of performance requirements, e.g., flight time, speed, altitude. Determination of the type of airplane, fixed wing, glider, jet, or VTOL or YAL, vertical takeoff and landing. Determination of the payload limit, e.g., camera, GPS, sensors. This stage lays the foundation for the subsequent technical design and ensures that all subsequent decisions are aligned with the functional and operational objectives. 2. Aerodynamic design and structure. Once the purpose and requirements are determined, the aircraft is designed according to aerodynamic principles. Specialized software such as SolidWorks, AutoCAD, or XFLR5 is used to model the structure and simulate airflow over the surfaces. Key elements. Wing selection. Different types of wings offer various lift/drag ratios suitable for gliders, training aircraft, or high-speed jets. Wing configuration. The wingspan, chord, dihedral angle, and sweep angle affect stability and control. Fuselage design. A balance is struck between aesthetic elements, durability, and internal space for electronic equipment and payloads. Control surfaces. The rudder, ailerons, and elevators are designed to provide adequate control. The design must balance weight, durability, and aerodynamic efficiency. 3. Material selection. Materials must be lightweight but strong enough to withstand aerodynamic forces and minor impacts. The choice of material directly affects flight performance, durability, and manufacturing complexity. Common materials: foam, e.g. EPP, Dupron, polystyrene. Lightweight, impact-resistant, and ideal for beginners. Balsa wood, traditional material known for its high strength-to-weight ratio. Carbon fiber, used in advanced models to increase durability and stiffness. Plastics and composite materials, used in the fuselage frame, propellers, and motor mounts. Material choice is usually a balance between cost, ease of processing, and performance. 4. Propulsion system and electronic integration. The propulsion system, electronic components, and control mechanisms are carefully selected and integrated based on design parameters. Propulsion system, electric motor, brushless DC motors are prioritized due to their efficiency and power-to-weight ratio. Battery, LiPo, lithium polymer. Batteries offer high energy density and high discharge rates. ESC, electronic speed controller, decodes the receiver signal to manage motor speed. Electronic components, transmitter and receiver. The transmitter sends user commands, and the receiver transmits these signals to the servo and ESC. Servo, small actuator that controls the control surfaces, e.g. rudder, landing gear. Flight controller, optional. In advanced models, it is an onboard computer that stabilizes flight and enables automatic navigation. The integration process ensures that components are placed in optimal positions to maintain balance and minimize electromagnetic interference. 5. Software development and control systems. Modern RC airplanes generally integrate microcontrollers or flight control boards that require embedded software or custom software. Even basic RC systems rely on software coding for control signals, control logic, functions, mapping signals between the transmitter sticks and control surfaces, stabilization algorithms for pitch, roll, and yaw angles using data from the IMU, inertial measurement unit. Automatic functions such as return to home, RTH, waypoint navigation, and geofencing. Open-source flight software like ArduPilot or INRV is frequently used, offering flexibility for customization and updates. 6. Assembly and manufacturing. This stage is the process of turning the design into reality, requiring precision and care to ensure that all parts are assembled correctly. The steps are as follows. Cut and shape the airplane frame parts using CNC machines, laser cutters, or manual tools with the selected materials. Install the electronic devices and wire the motor, ESC, servos, and receiver. Attach the propulsion system to the airplane frame using anti-vibration devices. Ensure that the center of gravity, CG, is within the design limits to balance the airplane. Secure and protect the cables, connections, and parts against vibrations and interference. This stage generally includes soldering, bonding, tightening screws, and checking mechanical connections to ensure that all moving parts operate smoothly. 7. Inspection and calibration on the ground. Before the flight, all systems are rigorously inspected on the ground to ensure safety and performance. The pre-flight inspection points are as follows. Verification of the range and direction of the servos. Calibration of the ESC to ensure the maximum throttle range. Radio range test to confirm that the transmitter maintains control within the intended distance. Calibration of the IMU and gyroscope, if present. Inspection of the electrical system to monitor current and battery status. Ground inspection helps identify potential failures and allows the pilot to precisely adjust the control settings. 8. First flight and repeated adjustments. The first flight takes place in a controlled environment, with good weather and ample space. This is an important stage to verify the entire design and manufacturing process. During the first flight, the pilot checks the responses of pitch, yaw, and roll. The balance is adjusted for stable flight. The performance of the engine system, climb rate, and stability are observed. After this flight, based on data and pilot feedback, several adjustments are made to the aircraft, and sometimes parts of the wing are redesigned to improve the center of gravity, servo path, or performance. 9. Maintenance, updating, and operation. When the controller is in operation, the unmanned aerial vehicle requires regular maintenance to ensure its lifespan and safety. Common maintenance tasks. Inspection of the structural durability after flight. Replacement of worn propellers, batteries, or servos. Updating the flight controller software or the data transmission module. Advanced users can integrate data transmission systems to monitor flight data in real time, or FPV, first-person view systems, for a more immersive control experience. Other users may enhance functions and update automatic capabilities for research or long-distance flights. 10. Safety and regulatory compliance. Piloting unmanned aircraft requires understanding and compliance with local air laws. The key points are as follows. Registration of the aircraft with the Aviation Authority, for example, the FAA in the United States. Compliance with altitude limits and no-fly zones. Do not interfere with the operation of manned aircraft. Ethical flight practices, respect for privacy, and ensuring public safety. Responsible operation protects not only the aircraft, but also the reputation of the broader community of unmanned aircraft pilots. Conclusion. The technical process of building a remote-controlled airplane is both an art and a science, requiring specialized knowledge in aerodynamics, mechanical structures, electronics, and software. This process begins with planning the idea and ends with iterative testing and operation. Advances in materials, microcontrollers, and wireless communication continue to expand the possibilities of remote-controlled airplanes. Whether a passionate hobbyist or an engineer, each airplane model is a small expression that accurately reflects modern technological capabilities and creative aspirations.